For decades, optimizing an industrial park meant one thing: geography. Manufacturers clustered factories near raw materials, rail lines, and each other to minimize supply chain friction. But the equation for heavy industry has changed. The overriding metric for a plant's survival is no longer basic geographic proximity, it is carbon efficiency. If a modern manufacturing plant attempts to reach zero emissions entirely on its own, it hits a mathematical wall. The barrier is CapEx, or capital expenditure. The sheer upfront cost of building dedicated green infrastructure is lethal to a standalone facility's balance sheet. To genuinely eliminate its carbon footprint, an isolated steel or chemical plant cannot just buy solar panels. It requires its own hydrogen electrolyzers for high-heat fuel, massive battery banks, and bespoke carbon capture units. Look at a single factory node on a grid. As independent green energy, hydrogen, and carbon systems are bolted onto it, the local CapEx gauge instantly overloads. The economics fail before the concrete is even poured. When you replicate this model across an entire industrial sector, dozens of isolated nodes, each paying a premium to build their own private infrastructure, you generate massive financial waste. Heavy industry requires immense, continuous power and chemical inputs. Forcing every plant to generate and balance these volatile loads in total isolation is structurally inefficient. The future of heavy manufacturing requires abandoning the standalone factory model entirely. Instead of isolated liabilities, the new model relies on extreme integration. Energy storage, hydrogen production, and carbon capture must be treated as shared public utilities. The costs and resources are distributed across an entire centralized park rather than shouldered by a single corporate entity. Without this deep integration, industrial decarbonization simply breaks the bank. A factory's financial survival now dictates that it physically connects into a shared, low-carbon ecosystem. Retrofitting legacy industrial sites to share these utilities is an infrastructural nightmare. Tearing up 50-year-old concrete to install communal hydrogen pipes or carbon networks carries astronomical costs. The economic alternative is to start with a blank slate. By planning new industrial corridors from the ground up, engineers secure a day-zero infrastructure advantage, embedding integration directly into the foundation. We can see exactly where this is happening on this map of India. The glowing nodes mark emerging, master-planned industrial zones. These sites present a massive opportunity to design total infrastructure symbiosis right from the start. Let's model exactly how this architecture is constructed on an undeveloped corridor, layer by layer. The first layer is integrated utility-scale renewable generation. We deploy wind and solar arrays directly to the perimeter, feeding raw electrical power into the central footprint. But heavy manufacturing runs continuously. As wind and solar output naturally fluctuates, the electrical supply cuts out, causing immediate failures at the receiving factories. To solve this, engineers introduce the second architectural layer, centralized energy storage. A shared, utility-scale battery facility absorbs the erratic renewable output. It acts as a massive buffer, discharging a stabilized, continuous microgrid flow directly to the manufacturing nodes. One central battery bank smoothing out the entire park cost a fraction of what it would take for 50 separate factories to build their own storage silos. This stabilized electrical grid is critical, but it only sets the baseline. It provides the reliable power necessary to run much heavier chemical processes. Certain sectors, like cement and steel production, require intense thermal heat. You simply cannot reach these extreme temperatures efficiently with electrical resistance alone. Manufacturers need a combustible flame to replace coal and natural gas in those kilns and blast furnaces, and it has to burn with zero carbon emissions. Shared power generation is just the starting point. True industrial decarbonization means leveraging this reliable grid to power the next phase, the heavy chemical infrastructure. To solve the high heat dilemma, the ecosystem relies on its third layer, centralized hydrogen production. Drawing directly from the park's continuous microgrid, a large-scale electrolyzer facility splits water into oxygen and pure hydrogen gas. Because the hydrogen is produced on site, it is piped immediately to the specific factories that require combustible fuel. No trucks, no extended distribution pipelines. Sharing this single production hub and piping network drastically lowers the individual CapEx. The cost per kilogram drops steeply. Even with zero-emission fuel, the actual chemical reaction of making materials like cement inherently releases carbon dioxide. You cannot avoid it, which necessitates our fourth layer, carbon capture. Point source capture units pull the CO2 directly out of the factory exhaust stacks. The gas is intercepted and routed into shared pipes before it ever reaches the atmosphere. But now the park faces an immediate logistical bottleneck. It is rapidly accumulating thousands of tons of localized captured CO2. The solution is the final and most complex architectural layer, circular carbon systems. Instead of paying to compress and bury the CO2 underground, engineers pipe the captured carbon and combine it with the park's shared hydrogen supply. This catalytic reaction yields highly valuable products. It creates synthetic fuels and complex chemical feedstocks, the exact raw materials heavy industry relies on. Those newly created synthetic feedstocks are then piped right back into the manufacturing nodes. The waste of one process physically becomes the raw material for the next. This creates a fully closed-loop mass and energy balance. The entire park operates as a single thermodynamic engine, continually recycling its own outputs. This deep structural interconnectivity mathematically drives resource waste towards zero across the entire geographic footprint. Energy and materials simply cycle through the grid. This highlights India's unique strategic advantage in building new corridors. Engineering these closed loops simultaneously from day zero is immensely more practical than trying to sequence them into legacy sites over decades. In a fully mature ecosystem, carbon waste is no longer a liability to be vented or buried. It is an essential, monetized input that powers the adjacent facilities. When we pull back from the microscopic engineering schematics, the massive macroeconomic impact of this new architecture becomes entirely clear. We can measure the legacy isolated model against the integrated park by looking directly at the data. This dashboard illustrates the structural contrast. On the left, the isolated model groans under high redundancy costs. On the right, the integrated model reveals massive reductions driven by shared capital expenditure. By pooling infrastructure, the overall cost of operating the integrated park drops permanently. Because waste is captured and treated as a localized supply chain, resource utilization pushes toward total efficiency. And because the implementation is centralized, the timeline for complete decarbonization accelerates sharply. Executing this on a global scale changes the mandate for infrastructure planners. Renewable energy generation, hydrogen electrolysis, and carbon capture can no longer be approached as distinct, siloed sectors. They constitute an industrial symbiosis. They are interdependent utilities that simply will not function economically unless they are master planned together. The factories of the future will not operate independently. Their financial and operational survival depends entirely on functioning as closely connected nodes within a synchronized, low-carbon ecosystem.